Good afternoon, guys. So let's start the class. So in the morning session, we were discussing about addition of halogens, right? And that happens via anti-addition. Anti-addition in the sense it happens like one alkane will be added from, sorry, one of the halogen of the halogen molecule will be added from two different planes. That's what anti-addition is. So the predominant way of addition of these halogens happens via anti-addition. And when we are performing this halogenation, for trans-butene, we end up with mesoisomer, and for cis-butene or for cis-alkenes, we end up having enantiomers. Like you'll get both dextrorotatory and levorotatory in the final product mixture. So yeah, I just shared the screen. So when we have like maybe when we write the Fisher projection and all, we will get to know the proper meso and trans and all. But in there is only one thumb rule actually. Both of them only way like in OP Tandon they gave sin addition also for this addition of halogens part. But when I was referring to Singh and Jagadamba, they did not include that part even in Singhage also. So we will follow only one type of addition, that is sin addition. So when the sin addition of halogens means, sorry, anti addition, where each bromine atom will be added from the another plane. As you can see, if this is the reference point, one bromine is added to this side and the another bromine is added to the other side of the plane. Like one is above and one is below. So when we are writing the Fisher projection, we have mesoisomer for trans, meso compound, anti-addition, you have meso compound, and for cis isomer, upon performing the same anti-addition, there are two possibilities. You can have dextrorotatory and levorotatory. So we will end up having a racemic mixture. You will end up having a racemic mixture. So I'll wait for some time. You can take down these. Anyway, I'll be sharing these notes with you. But you just write down trans-butene upon anti-addition of halogens will give meso compound. Cis-butene or cis-alkenes upon anti-addition of halogens will give racemic mixture or a pair of enantiomers in the product mixture. All right. This part was asked in the previous mains. This part they have asked. So how many stereoisomers are formed at the end of bromination of trans 2 butene? And the answer is only one, because one meso compound will be formed. 1 second. Yeah, that is one thing. Okay. So those are done writing, can keep the heading as addition of HOX, that is hypohalous acids. This part is also important, the one which we are about to deal. Even they asked in previous mains. This part, where is this? This they have asked in JEE mains. I don't remember the exact year, but they have asked. Next, please take down the heading as addition of next next addition reaction. Addition of HOX. HOX are nothing but hypohalous acids. Hypohalous acid. Even this was asked once in the exam. Direct equation they have asked. They did not even went into specifics, mechanisms or nothing. Just the question as it is they have asked. I'll discuss the question later, but let us see what exactly happens in hypohalous acids. So hypohalous acids are nothing but halogen atom bonded to OH. Okay, so in this one, what is the speciality of this reaction is generally what do we have? Whenever we have any halogen bonded molecules, we will attribute the negative charge to halogen and name it as halide part. The other one obviously becomes the cationic part. Whereas here, whatever the oxygen we are having, it will be more electronegative. In that scene an anti question, the question was number of optical isomers. No. In that addition part, the question was something like this: how many stereoisomers were formed? And the options they gave 1, 2, 3, 4. So how many stereoisomers? Need not to be optically active in the end. It should be how many will show stereoisomerism. Like how many of them will be observed at the end of the reaction. And the answer is 1 for this because you have only one meso compound. Answer will be 1. The internal optical activity will be 0 due to the internal compensation, and that internal compensation is due to the plane of symmetry. So next, yeah, as I was saying, the important part when it comes this they have asked. Okay, the question goes something like this. I'll 1 second. I'll give. Enantiomers are also stereomers. Correct. Enantiomers will be formed for cis. They were asking specifically for transbutylene. So that's why only one. If they gave cis 2 butene, then total you can make it as 2. One dextro and one levo. They were only asking for transbutene. That's why the answer is 1 for that particular question. Okay. 1 second. I'll admit people. I'll give you the question also what they asked in the previous mains regarding this hypohalous one. So very simple. They didn't even went into all the details. Like by looking at the molecule itself, you can write. Actually, I will tell you how to approach. Then I will give you the question. You give it a try. Okay. So the theory behind this particular question is addition of hypohalous acids to alkenes. So as long as we know alkenes are electron rich compounds, right? Because they have a weak pi bond and they are more reactive. Now when they are reacting with this hypohalous acid, okay, the X can be here chlorine or bromine or iodine. Fluorine will not involve. So this hypochlorous acid or hypobromic acid or hypoiodic acid, when they are reacting with the alkene, they will give us halohydrines. Halohydrines. What are halohydrine means? To the carbon-carbon double bond, one carbon will get OH, the other carbon will get the halogen part. So these are halohydrines. These are halohydrines. So how exactly this addition will happen? Because we don't know the mechanic, like depending upon the R groups or the type of groups attached to this carbon-carbon double bond will determine the position of addition of OH and H. So how do we do that? We will see in the next step. So what happens in this particular HOX molecule means the electronegativity of oxygen atom is greater than that of halogens. Why? Because we are not starting with fluorine, we are starting with chlorine, bromine, and iodine. So electronegativity of oxygen will be more. So because of that reason, the polarization of oxygen halogen bond will happen in this way. Oxygen will end up having delta negative and the halogen part will have delta positive. So this is the crucial step. If we don't know what will be added to the molecule to our alkene first, we cannot determine the product. Halohydrines. What happened, ma? What is the name of the product form? Halohydrines. Let's say if we take ethene, you will have ethylene chlorohydrine. I'll give you the example also. So yes, so in this the polarization will happen in this way. The halogen part will end up with positive charge and the OH part or specifically oxygen will end up with the negative charge. So let's take a simple example. So ethene CH2 double bond CH2 or ethylene on treating with hypochlorous acid. This is hypochlorous acid. Okay, what will happen? This will have negative charge and this will have positive charge. You have CH2, CH2, OH and Cl. So this is ethylene chloro ethylene chlorohydrin. So whatever the halogen we are using, you can just replace the halo part with that name. Can how can have 5 bonds? Sorry, double bond is not there. My mistake. Wait. Out of practice, I drew the double bond. No, double bond is not there. So ethylene chlorohydrin. So the double bond will be broken down, whereas OH group and chlorine will be added to the molecule, giving us ethylene chlorohydrin. Now, the type of question they have asked here is, I'll give the question directly. This was asked in 2016 mains. Wait a minute. This was asked in 2016 mains. They have asked in 2016. So the question is, the reaction of propene, the reaction of propene with HOCl, that is Cl2 plus H2O. I will let you know why we are writing separately also. Proceeds through the intermediate. Proceeds through the intermediate. So they gave the options. That options I'll give later because we haven't discussed the mechanism yet, right? So directly they gave. Oh, ma'am, is it chlorohydrate? Chlorohydrin, ma. Chlorohydrin, not hydrate. HYDRIN. This is IN. Ethylene chlorohydrin. So this reaction was asked, and here they were asking about the type of intermediate. And we all know whatever the addition reactions we are discussing, each and every one of them is electrophilic addition reaction, which means the first thing that will be added to the carbon-carbon double bond will be our halonium ion, that is chlorine with the positive charge. So if you take propene, that is one propene, CH3, CH double bond CH2. So what do we have? OH and Cl minus. OH will have the negative charge, Cl will have the positive charge. Now, between the shifting of this pi electron cloud, in the first step, whatever the step one we have, it will happen like this. The reaction of propene with HOCl proceeds through THRU or THROUGH through the intermediate THRU through. Wait a second, I'll write neatly. I'm using a lot of shortcuts today, sorry. Okay, so for us to understand what is the type of intermediate or what is the type of product that we will get, we have to follow the mechanism. So simply first and foremost step will be the addition of electrophile. Here the electrophile will be Cl plus, not OH plus, because that's illogical because the electronegativity of oxygen is more. So what happens in the first step is obviously the electron shift will happen in the another direction because there is alkyl group. So the electron pair will shift in this direction. So you have a negative charge and here you have a positive charge. So in the first step, the electrophile will attack, that is Cl plus, and that will attack on the carbon with negative charge. So we have CH3, CH plus, and CH2Cl. So after this chlorine is added, so this is slow step and the rate determining step. So this will be our reaction intermediate. This will be our reaction intermediate. So after this chlorine is being added, now comes the OH minus part. and that will get itself attached to carbon with the positive charge. So you have OH and you have CH2Cl. So this is our final product. And in the question, they are not asking the final product, they are asking the reaction of propene with this hypochlorous acid proceeds through the intermediate. So this is the answer. They gave a lot of options, but this will be our final answer. So the intermediate here will be secondary carbon, second carbon with positive charge on the second one and CH2Cl. So this will be the answer. This was asked in 2016 mains. Only if you know how to distribute the charges between OH and Cl, then only we can attempt this question. So the main reason for chlorine ending up with positive charge is because the electronegativity of oxygen is more. So here X can't be fluorine. No, X cannot be fluorine. It can be chlorine, bromine, or iodine. Only three. What is the IUPAC name of the intermediate? We go with halonium ion. I think N-propyl chloronium ion or something like that. N-propyl, yeah, N-propyl chloronium ion, something like that. They were not asking the names. They just gave this different arrangement of chlorine or different substituent OH. They were interchanging the positions of this chlorine and OH, and that's how the options were asked. Okay, so this is the answer. So simply you just have to give the charges based on electronegativity value and proceed with the reaction. Okay, so this is the mechanism actually. So in the first step, the electrophile will get attached to the negatively charged carbon, and that is the rate determining step. So since a positively charged chlorine is being added, it is an electrophilic addition. And in the second step, to the positively charged carbon, the OH minus part will get attached and we will get chlorohydrin, propyl or propylene chlorohydrin, something like that we will get in the final one. And yeah, this was asked only once, and that too in 2016 mains they have asked. Okay, and as I was saying, either we can directly use HOX or else we can use chlorine, any of the halogen gases in presence of water or aqueous solution of chlorine, something like that. So either we can use the notation HOX or we can use H2/H2O, which means aqueous solution of the halogen gases. Means the halogen gas will be bubbled through the water, and for that momentary of time we will be performing the reaction. And the order of reactivity, we already ruled out the fluorine. So whatever the halogens that are involving in this particular reaction, follow the order. So first comes chlorine, then comes bromine, and then comes iodine. Or else we can use the another notation also. Cl2/H2O or Br2/H2O or I2/H2O. So greater than. So chlorine will be more reactive towards this addition of hypochlorous acid, will be more reactive than bromochlorous acid or iodochlorous acid. Bromo, and yeah, as you are asking, in practicals we will be prepare alkanes and alkenes and no, we will concentrate on aldehydes, ketones, mostly second year point of view only will be there in practicals. Alkanes, alkyls and all we won't prepare actually. Second year part will be included under the practicals. No, you won't do this actually in the lab. So this is hypochlorous acid, addition of hypohalous acids giving us halohydrins. So how are we deciding the reactivity of hydrogens? Maybe based on the electronegativity, because the entire addition reaction is happening on the effective distribution. Acha, even that will be iodine part. H2 greater than Cl2 greater than Br2 greater than I2, hypohalous acids. Mm, actually, I didn't look in that point. I will let you know what can be the reason, because bond dissociation enthalpies cannot justify this. I will let you know in next class, okay? Why exactly is this particular order? I will let you know definitely. All right. So as we were discussing, this the same addition of H and OH can be done even for cyclic compounds also. Okay. So if we have double bond and we are using any mixture, let's say Br2 in presence of H2O, so the type of product form will be, since whatever carbons we have, they are of equivalent, so there is no need in discussing this will be the stable or this will be uh, how do you say less stable, something like that. So we can just go on with the addition of our halogen part and OH part on the other side. So when it comes to cyclic compounds, we have planar structure, right? So we end up having enantiomers because this is a tertiary carbon, right? So there will be one more hydrogen. So you have a chiral center over here and you'll have a chiral center over here also. So mostly this reaction of cyclic alkenes with these hypohalous acids will give us enantiomers, because you have already a secondary carbon, right? To that you are adding a bromine, so probably we might end up having chiral center, so leading us to two possible products. So for cyclic compounds they might give us enantiomer, a pair will be formed in the product mixture. So if that is endocyclic, whereas if the double bond is exocyclic in the sense some alkylidine type. So you have a cycloalkane added to that. If you have a double bond, something like this, then it varies, like maybe one chiral center or something like that. So let's say we are performing the same combination, Br2 or H2O. So what are the sites of addition? This will be 1 and this will be 2. So which will give a stable carbocation. Here we have 1, 2, 3. This will be the tertiary position and this will be the primary position. Obviously, the positive charge is more favored on the tertiary carbon. So whatever the bromine or halogen part that we have, it will be added at this position, and OH part will be added at this position, because that is with the negative charge rate, OH minus, and positive charge over here. You have CH2Br. So how am I deciding that we are supposed to add OH minus at this position? Means the intermediate is our carbocation, right? So the carbon involved in the double bond, this is tertiary, and this terminal carbon is primary. Obviously, if you have positive charge on the tertiary carbon, that will be a better stable carbocation. So to carbocation, the negative part, the nucleophilic part of the reagent will get added. So that's why we have OH added on the ring, and the bromine will be added to the CH2 part, to the exocyclic or to the other methylene group, that is CH2 group. So this will be the only product, major product. This will be the only product because we are going with the stabilities. Here why we are not having the major product means both are secondary carbons only. This is secondary carbon, this is also secondary carbon, so equivalent position, but you will have the chiral center after the addition is finished. That's why you'll end up having an enantiomer. But whereas in here this will be the only product, I guess, not even major, it will be the only product because of the stability factors. So that's how you have to decide. So almost every addition reaction except for anti-Markovnikov's rule were happening depending upon the stabilities of carbocations, where tertiary is more stable and secondary than primary. So accordingly, we have to judge and move forward. Only logic is what is the uh, electrophilic part in our reagent and where it should be added, so that we will have a proper or a better stable carbocation. So in our reaction, we have bromine as our electrophilic part and the nucleophilic part is OH minus. So this will be added onto carbon with a negative charge, and this OH minus should be added onto carbon with positive charge. But since we are on electrophilic addition, the electrophile will be added first. After electrophile is added, obviously we have to look for stable carbocation, where tertiary is more stable than secondary than primary. So accordingly, we just have to add the OH minus part in that position. So I'll give you an example. So for this one, what is the final compound that we end up with? So let's take some Cl2 in water. So what will be the final product? Where will OH is added and where is the bromine is added? The bromium ion, Br plus in this one. So this is our tertiary carbon and this is our primary carbon. So where does the bromine, to what carbon bromine will attach and to what carbon the OH minus part will attach? Cl plus will add to what, ma? Primary carbon or tertiary carbon? Are you there? Am I audible to you, ma? Mm. So yes, yes. Okay, if I am audible, please tell me. Acha, you told yes, correct. The chlorine part, the Cl part will get attached to the primary carbon because that will give us a stable carbocation, which is a tertiary carbocation. So to this carbon with positive charge, our OH minus will get attached. So this will be the final product. So accordingly, you have to decide. All these are as like whatever the reactions that we are seeing, all these are electrophilic additions only. First attacking reagent or the first reagent that will be added will be electrophile, the one with positive charge or electron deficient. So that's the major hint you have to understand. Based on that, you can decide the reagent intermediate, the reactive intermediate. Okay, so this is about addition of hypochlorous acids, giving us halohydrines. And these halo can be either chlorohydrines, bromohydrines, iodohydrines, whatever it might be. They can be due to the mixture of chlorine and water or halogens and water, or directly we can take the hypohalous or hypochlorous, like hypohalous acids we can directly take. So this is the reaction. So the mechanism and all, like, things are very simple. Only thing is we should have clarity what will result what type of carbocation. That is the only way to decide the major product or the stable reaction intermediate. Okay, so the next thing is reaction with dilute H2SO4. So the next chemical property is reaction with dilute H2SO4. So in this reaction of dilute H2SO4, two different things will happen. First thing is, as far as we remember, H2SO4 is a dehydrating agent, right? But in this particular reaction, the net reaction will be due to addition of hydrogen and addition of HSO4 as HSO4 minus and H plus on our molecule. And further there is rearrangement, that part I will tell. Why do we have to write Cl2 slash H2O? Shouldn't we write HOCl? We can write HOCl is the proper hypochlorous acid. The reason why it is forming means by bubbling these halogen through water. It will be a moment like in the mixture itself, the water halogen or the water chlorine mixture itself is hypochlorous acid. So we either can write HOCl or Cl2 slash H2O. Both of them are the same thing because when water interacts with HCl, we have HX and HOCl. I'll show you here. Because when chlorine reacts with H2O, you'll have H plus and OH minus, right? So you have HCl and HOCl. So this will be very unstable. Unstable in the sense this is the one, this is hydrochloric acid and this is hypochlorous acid, where +1 charge and this entire thing will have -1. Here you have -1 and +1. So this will be our acid. So we can write this mixture or else we can directly write HOCl. There is no wrong. Both of them will indicate the same thing. Addition of chlorine as Cl plus and addition of hydroxyl group as OH minus. Okay, so this reaction will be very interesting, and from here only we will understand about this particular one, hydroboration oxidation reaction. But what happens to the remaining H plus and Cl minus? It is in aqueous solution, right? They exist as, okay, good, very good. It is an aqueous solution, no? They exist as H plus and OH minus only. All right. So what happens when we react alkene with dilute H2SO4? So let's see that part. So alkenes gives electrophilic addition, which means the H plus part will be added first. Gives electrophilic addition, with cold sulfuric acid, and the addition reaction follows Marconi-Kob's rule, and the addition reaction follows Marconi-Kob's rule. So if you take any alkene, RCH double bond CH2, something like this, and if we are treating it in presence of sulfuric acid, we have H plus and HSO4 minus. H plus part will be removed as proton and we will be having hydrogen sulfate. It's conjugate base. So what happens is, according to the Marconi-Kob's rule, the hydrogen of the reagent will be attached to the carbon having more number of hydrogens. So the same thing will happen here also. So this is our skeletal reaction, right? So according to the Marconi-Kob's rule, what will be added first? The electrophile, that is our H plus, will be added to the carbon containing more number of hydrogens. So this terminal CH2 will be converted into CH3, and here you will have a positive charge, obviously, because electron shift will happen in this direction, and another carbon will be added by HSO4. So this is called as alkyl hydrogen sulfate, because the sulfate, if both the protons are removed, then only we can call it as proper sulfate, but there is one more hydrogen intact, so that's why we are calling this is alkyl part and this is the hydrogen part, alkyl hydrogen sulfate. So this is the net reaction. The hydrogen of coming from the acid will be added according to the Marconi-Kob's rule, where it will be added to carbon having greater number of hydrogen atoms. So because of this, we will be getting alkyl hydrogen sulfates. So let's take a simple example. Let's start with propene. If R is CH3, you have CH double bond CH2. So in presence of H2SO4, you have H and HSO4. So what will happen? This H will be added over here and the HSO4 will be added onto the secondary carbon. So you have CH3, CH3, and over here you have HSO4. So this is the isopropyl group, right? So we have isopropyl hydrogen sulfate. But this is not the end of the reaction, because there is an extension for this hydrogen sulfate which are formed due to addition reaction, and that part is very important. What happens is that whatever the alkyl hydrogen sulfates that we got, alkyl what's happened yeah alkyl alkyl hydrogen sulfate, whatever we got in the above reaction, on hydrolysis. Hydrolysis means on treating with water will gives us alcohol, gives alcohol, and acid, sulfuric acid will be regenerated. So if we take the same above reaction, that is isopropyl hydrogen sulfate, which is CH3, CH, HSO4 and CH2 on hydrolysis. Hydrolysis in the sense addition of water. What will happen wherever these, sorry, this is CH3. So wherever we had HSO4 minus, that will be removed. How it will be removed means water will be H and OH minus na. The replacement of HSO4 will be done by the OH. This acid will be removed with this H plus as H2SO4, and we have CHOH and CH3. Nothing is happening over here. Whatever the HSO4 we have, it will be removed as H2SO4, and that H plus is coming from the water molecule. And its initial position, this HSO4 position will be occupied by the OH group. So what do we have if you try to write the net reaction? We had propene initially. What do we have? Propene, that is CH3 CH double bond CH2. On treating with sulfuric acid, we got isopropyl hydrogen sulfate, which is CH, HSO4 and CH3. So this on hydrolysis, we are getting simply propane 2-ol, OH, and this is CH3. So from here, prop 1 in, we are converting into prop 2-ol. So this is the importance of this reaction. From alkenes, we can convert them into alcohols by treating them with sulfuric acid followed by hydrolysis. This part is very important. How can we convert alkenes to alcohols means by treating with by treating them with sulfuric acid. Subsequent hydrolysis will give us alcohols. So I'll wait for some time. You please note these reactions down. And from there, I will tell you an important point. Why? Because we are starting with substituent or some unsaturation between first and second carbon. And we are ending up with alcohol group at the second position. So is it possible for us to get prop 1-ol, propanol, not prop 1-ol, propane 2-ol? Is it possible for us to get prop 1-ol? Can we add this OH group on the first carbon, because the unsaturation is between first and second carbon, but even we are not ending up with the mixture of propane 1-ol or propanol, 1 propanol, 2 propanol. We are only getting 2 propanol. So is there any possibility for that? Means yes, that happens via a different course of reaction called hydroboration oxidation. That is a lengthy process. But before we go over there, I'll wait for some time. You write these reactions down. Yes. What happened? Repeat what I said. Okay. So we are starting with prop 1 in, where there is unsaturation between carbon number 1 and carbon number 2. Formation of alkyl hydrogen sulfate is fine, and formation of propanol, that 2 propanol is also fine. So we are looking for a possibility. Since we have the unsaturation between first carbon and second carbon, there should be a possible formation of 1 propanol also, right? So but that formation of 1 propanol is not at all feasible by this particular reaction. We have to follow another reaction. So in presence of sulfuric acid and followed by hydrolysis, we will get alcohols from alkenes. This is the commercial preparation of alcohols actually, because we have a lot of hydrocarbons, natural sources like petroleum, all this pyrolysis and all. If we perform petroleum, coal, everything, we will end up having alkenes, right? These alkenes, by like hydrogen sulfuric acid is also cheap. So simply they will perform the reaction, and after that they'll hydrolyze it and they will prepare alcohols. Obviously there is a difference between 1-ol and 2-ol, but this is a commercial preparation of alcohols actually, like easy preparation of alcohols from alkenes. Okay. So 1-propanol, how to prepare that, I will tell you in the next one. That is a hydroboration oxidation reaction. That part is important because intermediate steps are there and bigger mechanism, everything, lot of things to take down in that. That's why. Please let me know once you are done. Till then, I'll be waiting. That's why. Someone just left the meeting. Who is that? Okay. So keep the side heading next as preparation of 1-alkanols. Preparation of alkane 1-ol from alk 1-ene, because from propene we got propane 2-ol, not propene 1-ol. So in this particular step we are trying to get the same OH group substituted at the first position, because there is equal unsaturation between first and second carbons, right? So there should be a possible way to prepare 1 alcohols, that is the primary alcohols also. So that can be done by the next and important reaction is hydroboration, hydroboration oxidation reaction. This reaction is very, very, very important. We can expect at least one question in the phase test. Okay, so understand carefully. So hydroboration oxidation reaction. So from the name itself, there are two things that should be obvious. That is hydroboration means we are adding hydrogen and borane. Like mostly we'll be using borane. Mostly they go with diborane, but writing the regular BH3 will also satisfy our reaction. So we will be adding borane and oxidation part. So how can we perform this oxidation? So this is step 1 and this is step 2. So step by step we will see in the next step. So what happens is that I'll give you the statement and step by step I will let you know the mechanism. The addition of borane, the addition of borane means BH3. The addition of borane to an alkene, to an alkene followed by reaction with, followed by reaction with a base, followed by a reaction with a base, that is OH minus and hydrogen peroxide, because the oxidation half is done by The oxidation step of the reaction will be done by the hydrogen peroxide, H2O2, is called hydroboration, hydroboration oxidation reaction. No need to write the entire name, you just write HBO, hydroboration oxidation reaction. So how can we do that? Because lot of reagents are involved. We are using diborane, we are involving a base, we are saying that we are further oxidizing it. So how can we do that? So in order to make it simple, let us do step by step only. After I'll tell you the mechanism, I'll give 10 minutes break, and then we can start at 3:30. Okay, or like, yeah, we can start again. So I'll just give you the steps. Explanation I will do after the break. So I told you, right, there are two steps in this reaction. Step 1 will be addition of borate. Addition of borane. So this step is the hydroboration part, the HB part. Hydroboration part. So what do we have? We are telling that we are taking alkenes, right? Our alkenes will be RCH double bond CH2. And the involving borane will be BH3. Diborane also we can take, but it's better to take normal borane, that is BH3. This will be electron deficient. So what will happen? The alkyl groups, the pi bond, this is electron rich, right? So this pi bond will be broken down and we will be getting alkyl borane, RCH CH2 BH2, right? So this is alkyl borane, and borane has the valency of 3, right? So we can add 2 more alkyl groups, RCH double bond CH2. So end of the reaction we can get trialkyl borane. This is trialkyl borane. This is very important because the course of the reaction will be different if we are using hydrogen peroxide in this step, and it will be different if we use some acidic acid in the next step. So that's why this trialkyl borane formation from addition of alkyl groups to boron will be important one. The carbon, it's not satisfied. Wait, 1 2 3 4, 1 2 3. The fourth bond will be with the boron, right? Wait, yeah, hydrogen will be added to this one, no? Sorry, in here. Wherever the whatever the hydrogen the boron is losing, that will be added to this second carbon. So yeah, so alkyl part, trialkyl borane will be formed, RCH2CH2. 3 such alkyl groups will be added, giving us trialkyl borane. So the next step is crucial because this, if we do a small mistake in the step 2, it will alter the product. So whatever the trialkyl boranes we have, RCH2, CH2 taken thrice, trialkyl borane we have, we will be treating them with hydrogen peroxide in presence of a base. Like both the reaction with base and hydrogen peroxide happen simultaneously. So the boron, whatever the boron we have, that will be converted into boric acid. Okay, or the boric acid. So the rest of the alkyl part will be oxidized because we are performing the oxidation reaction, right, in the step 2. That will be resulting in alcohol formation, RCH2OH. That is primary alcohol formation because we have terminal double bond. So what is this step? Oxidation of trialkyl borane with hydrogen peroxide in base or in basic medium, H2O2 in basic medium gives alcohol. So this is the step 2. So no need for complex mechanism or not. In the first step, alkyl groups will be added, alkene will be converted into alkyl group because boron has the valency of 3, 3 such alkyl groups will be added. So in the second step, we are oxidizing by what? By using hydrogen peroxide in the basic medium. So boron will be forming orthoboric acid and the alkyl part will be oxidized to primary alcohols, giving us primary alcohols. So this is hydroboration oxidation reaction. So you guys have a break. I'll be on mute. What's the time? You can take 10 minutes break. It's 25, right? So we will start our class again. Sorry, it's 2:33. We'll start at 2:30 or 2:35. We will start. Okay, I'll fix the time. We'll start at 2:30. It's fine. So till then, I'll keep the screen on only. Those who are still writing, they can write it down. Others can have some water or snacks and be back by 2:30. All right. Actually, this is the continuation of the previous one, but they treat this hydroboration as separate reaction actually. But you can keep it as continuation only. Anyway, we are preparing alcohols only, right? Okay, do the continuation only because we are coming to this hydroboration reaction because we were unable to prepare all primary alcohols. So do the continuation only, but this reaction is very, very, very important. Okay, go for a break. Be back by exact 2:30. Then we will continue. Yes. Yes, I'll give ma, because before we go for hydroboration in cyclic compounds, we have to establish how come this H and OH, like what is the net reaction, in what manner the H and OH are added. So that part I will tell, and after that I'll give example for a cyclic compound, definitely. Okay. So I hope everyone got back, right? You just message, ma'am, we are back. Otherwise, I'll wait for some more time. All right, chalo. Let's continue. So, as you can see, we are performing the addition of, definitely we are converting an alkene to alcohol. So, the net reaction, if we write, we will understand two things. What are the actual groups that are added? So, I'm just combining the step 1 and step 2 so that we will try to write the net reaction. So, we have alcohol, sorry, alkene, CHR, CH double bond CH2. So, in the first step, we are adding boron, and because of that we are ending up with trialkyl borane. And in the second step we are treating with oxidizing agent, that is H2O2 in presence of a base OH minus. So what is the final product that we have are CH2 CH2 OH. So whatever the net reaction we have, it is addition of H and OH to carbon carbon double bond. Yes or no? Because initially we had a carbon carbon double bond between 1 and 2. In the next step we have a hydrogen and we have OH group. So this hydroboration oxidation reaction, the net reaction will be addition of H and OH to the carbon carbon double bond. And as you can see, anyway, hydrogen and hydroxyl ion, H plus and hydrogen and OH are added. So what rule they are following? Because whatever the hydrogen that is added to carbon having less number of hydrogen, which means what rule they are following? This particular hydroboration oxidation is following anti-Markovnikov's rule. So whatever the addition of H and OH is happening, it is by anti-Markovnikov's rule, because our OH group is attached to the terminal carbon and the hydrogen is attached to the inner carbon, which is having less number of hydrogen, which is opposite to Markovnikov's rule. That is, this hydroboration oxidation reaction will be following anti-Markovnikov's rule. That's the important point you have to note down. And when it comes to cyclic compounds, whatever the addition of H and OH, they are being added, they happen in what manner? They happen in syn addition, means they will be added on the same side of the plane. I will give you an example, don't worry, but just note down the points related to this hydroboration oxidation. So first thing is what rule they are following, the addition mechanism. Second thing is in what way both the H and OH are added. So let's take a simple example. The only logic is in hydroboration, they will give you the reagent and they will use one more here slash THF. THF is nothing but tetrahydrofuran. So this is just a reagent which helps for alkyl groups to react with diborane. So just it helps for the addition of these alkyl groups to the boration. Like it just helps in the step 1. So they will be using this slash THF most commonly in this HBO reaction. So simply alkene will be converted into alcohols. Most of the cases, they will be following anti-Markovnikov rule, where the hydrogen will be added to the carbon containing less number of hydrogens. Carbon having less number of hydrogen. So let's take propene as our example. So CH double bond CH2. So what is the net reaction? So we have BH3 in presence of THF, and in the second part of the reaction will be oxidation, H2O2 in presence of a base. So our product will be Markovnikov's rule. We will be following, right? So according to the anti-Markovnikov's rule, hydrogen will be added to the carbon containing less number of hydrogen, which means in the second position. And obviously the alcohol group will be added, the OH group will be added to the terminal carbon. So we have prop 1 in, and we are ending up with propane 1 all. So all this entire reaction is just to get one propanol from one propene. So all this stuff is just to get primary alcohols, because where did the OH group get attached? Primary carbon, right? So this is a primary alcohol. So most of the cases, whenever you have terminal double bond, then according to this we will have primary alcohols. So just a clarification, like it is obvious, but just we are making a point, because the OH group is attached to the primary carbon right here. So I'll give one example. Please tell me the product. After that we will see for cyclic compounds. We have CH3 taken twice, C double bond CH2. So same reagents 1 and 2. What is the final product? Ma'am, could you explain about the point regarding cycle? Yes, I will explain. I just made you to write down. I will explain in the next part when I'm explaining with example. I will explain. Don't worry. I will explain. So our first reagent will be, don't forget to write the reagents. Reagents are very important. I told you, right? Especially the second part of the reaction. If we miss this H2O2 in presence of a base, the course of the reaction will be different. We end up with alkanes, not alcohols. That's why the second reagent is very, very important, oxidation part. Okay, so what is the product here? So this is the skeletal structure CCH2. So what adds to what? This is our quaternary carbon, and this is our primary carbon. That does not affect actually, because this is following anti-Markovnikov's rule, right? So you just have to consider where does this hydrogen is getting attached. So to the first carbon or the 2-methyl propanol. Very good. 1, 2, so tertiary, not quaternary. So we'll have hydrogen attached over here, OH attached over here. So we have 2-methyl propane 1 all. So 1 propanol we'll have. So write one more. So we have take one more, but instead of terminal double bond, I'll give inner double bond. So CH double bond, wait, CH3. How is the intermediate trialkyl borane formed? I told you, right? Here you'll have, like, it will be it looks something like this. CH3 taken twice, CH2, CH2, no, only one hydrogen, because we two alkyl groups, right? So this entire thing taken twice, D. So this will be the intermediate. why we follow anti-Marconi-Cobb's rule. Why we are following anti-Marconi-Cobb's rule means whatever hydrogens we are getting, sorry, what wherever the hydrogen we are adding it to the higher carbon. That is because during the trialkyl boron formation, the hydrogen will be coming from boron. Okay, so there itself the hydrogen will get added to the higher carbon. That's why this is following anti-Marconi-Cobb's rule, not to the carbon containing more hydrogen, but exact opposite. The hydrogen is added to carbon containing less number of hydrogen. That's why here we are getting anti-Marconi-Cobb's rule. If you observe the mechanism, you will understand. Hydrogen itself is added in the first place to the secondary carbon. That's why. Yes. So here also give it a try for this 1 and 2. What is the product form? This is a single bond, not a double bond. So here you get to write like exactly apply the anti-Marconi-Cobb's rule in this example. 4-methyl yes. So we have carbon carbon double bond over here. So carbon will get okay BH3 THF, we have H2O2 OH minus. So our skeletal structure is something like this: C, CH, CH3. So we have CH3 as a substituent. So according to the anti-Marconi-Cobb's rule, the hydrogen will get attached to the one containing less number of hydrogen, and the alcohol group will be attached to the next one. So 1, 2, 3, 4. So we have 3-methyl butane 2-ol. 3-methyl butane 2-ol, not 2-methyl, no, no. It's not pentane also. Yes, yeah, you corrected. Fine. So this will be our final product where the hydrogen is attached to the carbon containing less number of hydrogen according to the anti-Marconi-Cobb's rule, and the other one will be default OH. So this is for normal open chain compounds. So what happens to the cyclic compounds? There are two ways we can deal cyclic compounds. So first let's see exocyclic alkane means methylidine compounds, and then we will go for proper cycloalkenes. So we have C double bond CH2, same thing. BH3 THF you have, and in the second thing you have oxidizing H2O2 in presence of OH minus. So just apply the same anti-Marconi-Cobb's rule and give me the product. Here it won't affect the stereochemistry. The how they are added, that doesn't affect. But in the next example, we have to consider one more point also. I will tell you what that point is also. But as of now, just do for the first methylidine cyclohexane. Okay, no need to tell me the whole compound. Just tell me where does the OH will get attached, on the ring or to the CH2 part. CH2 part or onto the cyclohexane ring, the OH part will be added or the H will be added. Yes, OH2 will be added to the CH2 part. Why? Because according to the anti-Marconi-Cobb's rule, like this is the skeletal structure. two things should be added, one over here, another onto the CH2 group. According to the Antonov-Markovnikov's rule, hydrogen will be added to the one containing less number of hydrogen, that is the carbon containing less number of hydrogens. So this is our tertiary carbon and this is our primary carbon. So hydrogen will get attached to the tertiary and the other end, free end, the CH2 will be having OH. So this is our final product. So here, just because we are having a carbon on the double bond and we have obvious, there is obvious relationship, like to what carbon we have to add the H plus. Whereas in the second compound, we are having a carbon double bond where both the carbons are belonging to the ring. So in this case, we have to consider the syn addition. Syn addition in the sense both the hydrogen and OH groups are added onto the same plane or added onto the same plane. So in like cis and trans, we will write, right? So like that we have to write. So if I change the writing of this compound, so here we have CH3. Yes or no? Like just say there is down the plane CH3, and this is our carbon number 1 and this is our carbon number 2. So between carbon number 1 and carbon number 2, which carbon is having less number of hydrogens, 1 or 2? Obviously 1, because that is a tertiary carbon. So hydrogen will be attached in this position and the OH will be attached over here. So by default you will have hydrogen belonging to the ring. So this is the product. So this is trans compound. So this will give trans because the OH group, the substituents, this is a trans. Wait, yeah, correct only. So the bulkier groups are above and below the compound. So trans or anti-product we will end up. So the thing is OH and OH are added on the same side. Don't get confused with this hydrogen. This is the hydrogen. The boxed ones are the ones that we have added. They are added on the same plane. So you can either write this way or else this way. CH3, H and OH. Maybe this will give you the clarity. This is the OH and the H that we have added. If you get confused by this, write the second way. Okay, so this is about hydroboration oxidation. So the entire aim of this reaction is to get primary alcohols from terminal alkenes. That too, one all mostly, one alcohols from one alkenes. All right. So I told you that the reagent, the second part of the reaction, the oxidation half is very, very, very important. I told you, right? Why means the same hydroboration oxidation reaction, if we alter the second reagent, they will give us the corresponding alkenes. Okay, so make a small note and take this down. So trialkyl borane reacts with organic acid, especially the most commonly used is simple acetic acid only, to give corresponding alkanes. Here also we follow anti-Markovnikov rule, but how H and H is already specified and how H is all specific, right? They are added. See, that's why I told you this is the hydrogen we are adding, right? So this is a tertiary carbon, yes or no? Tertiary carbon does not have any hydrogens at all. So this is our incoming hydrogen. Here the boxed hydrogen is the incoming hydrogen. This hydrogen is already on the ring. That's why you take down this one, where we are specifically writing the added groups OH and H, and they are adding in a they are added on the same side of the plane. That is the syn addition. So that's the one more point to be noted down. So here how H and OH is specified, right? That's why I ignored the second hydrogen which is already present in the second uh, structure. So you please take this down, you'll understand. You got it right. I'm not specifying, I'm just adding at wherever they are supposed to be added. The least numbered hydrogen containing carbon. That's it. Okay. Obviously, we cannot know what hydrogen is exactly being added once the final molecule is formed. Okay, coming back, trialkyl boranes react with acetic acid mostly. They will generalize it as organic acid. Acetic acid will be fine. So to give corresponding alkanes, so we have RCH double bond CH2 on treating with borane and THF. This part remains same, but the second reagent will be CH3COOH. So you have RCH2 CH3, means two hydrogens are added in this reaction. Yes, here also correct, Nana. Here also we are using anti-Markovnikov rule only. No change in the basic mechanism. Whatever the addition of H and OH happens, it is according to Markovnikov's rule only in hydroboration oxidation reaction. Okay. So this is a simple alteration to the above reaction. So if we have acetic acid instead of peroxide, instead of getting OH, because it will anyway, the hydrogen is already added in the trialkyl part. So in the second half, instead of OH minus getting added, the H plus will be added onto this terminal carbon, giving us an alkane. So this is just one simple note. That's why mentioning the reagent in an order is very important. So you have to mention, they'll mention the number also. In the same order, you have to follow. What is the first reagent that you are using? You have to number it as 1. What is the second reagent you are adding? So you have to number it as 2. Then only you will get to know that this is a two-step reaction where two different reagents are used to get the final product. So this specification is important. Okay. All right. What's the time? Okay, we have half an hour more. So I think we can finish one more property, and tomorrow we can see. Ozonolysis we will do tomorrow because that is very important and they have asked it twice. So we will do that freshly tomorrow. We will go to the another part, oxymercuration or simply hydration of alkenes. This is simple only, very simple when compared to this hydroboration part. Okay, take down the next property. I forgot the number, you number it. Hydration of alkenes. So hydration of alkene means we are adding proper water. We are performing the addition of water molecule to the alkenes. Acha, 5. Thank you, Ma, very much. Property number 5. So hydration of alkenes. So this reaction is also important actually, because here also we will be performing an alteration, like a deviation where we will be introducing oxymercuration demercuration part. So before I complicate things, let's just write the statement. In presence of an acid catalyst, in presence of acid catalyst, mostly we will be using sulfuric acid, H2SO4. Okay, so in presence of acid catalyst, alkene gives addition reaction. Alkenes gives addition reaction with water. So what is water? H2O, right? So H plus and OH minus will be added. Okay, so how come they are added means they follow Markovnikov's rule. Addition following Markovnikov's rule. Following Markovnikov's rule. So if you take a general alkene, RCH double bond CH2. So we have water. How can we write it? H plus and OH minus. So in presence of an acid catalyst, that is H2SO4. So according to the normal regular Markovnikov's rule, will the carbon be attached to first hydrogen be attached or added to first carbon or second carbon? It will be attached to the first carbon, because according to the Markovnikov rule, hydrogen H plus of the reagent adds to the carbon containing more number of hydrogens. So in the first step, this is our skeletal reaction, right? So the hydrogen gets added over here and OH group will be added to the another position. So this is our alcohol. So hydration of alkenes is giving us alcohols. All right, there is rearrangement, but that part we don't need to concentrate now. So in presence of an acid catalyst, when we perform hydrolysis reaction for alkenes, we end up having alcohols. Okay, so how can, okay, let's take a simple example. After that, I will tell you the mechanism. Or else let me give you the mechanism here itself, because the mechanism is also easy to understand. Because this is an electrophilic reaction, obviously, first step will be addition of CH2. So, sorry, to the CH2, H plus will be added. So, where will it add? To this carbon. So, you have R, CH plus and CH3. Now, here there will be one more water molecule coming from the mixture. So this water molecule will directly get attached itself. So I'll show you how also. So R, CH, CH3, and there is a positive charge on carbon, right? And there is a lone pair on the oxygen. So that lone pair will interact here. So we have O, H, H with the positive charge. So in the next step, H plus will be removed. We have R, CH, OH, CH3. So this is the reaction, single line mechanism. Simple. First H plus gets added, then water molecule will be, the oxygen will interact with the carbocation part, then this lone pair will be withdrawn and this will be removed as H plus, and you have your final alcohol. So this is the mechanism. So if you take a simple example, take propene, CH3, CH double bond CH2, this on acid catalyzed hydrolysis. What is the product formed? What is the product formed? Yes, simple. It will be 2-propanol because the hydrogen adds to the primary carbon and OH adds to the secondary carbon. So from prop 1 in, again we are getting propane to all. Propane to all. So this is one thing. So there is also one more extension to this. Achha, a lot of new things are there, but fine. So what happens instead of water molecule, if he has alcohol, because even alcohol will be producing proton, right? So what happens? So we have CH3, CH double bond CH2. We have CH3, O and H. This will be the positive part and the negative part. So give it a guess, what might be the final compound? Same way of addition, only thing is instead of OH, we will be adding the ester group, OR group, where I told you the answer. But tell me the final name. So you have CH, something like this. So obviously the H will get attached over here. So whatever the alkoxide part we have, CH3O. Wait a second. So we will be getting OCH3, ROR, R OR we'll have. That is, what is this? Ethers we will have, ROR we will have. Same mechanism, only thing is instead of OH, alkoxide ions, CH3O minus will be added to the carbon. So this is one thing. So again here also, there is one more named reaction called oxymercuration demercuration reaction, which gives us a better hydration. Acha, I want to tell a new reaction. Are you in a position to listen, or can we do this tomorrow? Because I can go on, but if you're not understanding, there is no point in me teaching. So will you listen, or do you need a break for some time? You can be open, because I cannot move on, right? If you are break, okay, fine. Break for some time. Okay. Meantime, I'll tell you a small incident. Okay. Yeah, I'll give a break for 5 minutes, ma, and then we will continue. Meantime, if you are interested, I'll tell you a small incident that happened when I was in college. Yesterday, I was talking to a friend from college. So this incident happened in my BTech second year. So we took permission for industrial tour, okay? But apart from visiting industry, we did all sorts of things in Bangalore. Like we went to Wonderla, we went to we went for trekking in Coorg. So this incident happened in Coorg. So we had an unplanned trek, okay? So in that unplanned trek, we happened to go to a nearby small waterfall. Most of us don't know swimming, so we was staying on the shore, and then this guy comes. No, no, no! You came to the waterfall. You are not supposed to stay on the shore. Just come inside. We will take care. Even if you don't know swimming, we will take care. Then we went inside. We were enjoying everything. All of a sudden, a snake appeared. Okay, we were in the middle of the water. Then there's a snake, like around 6 to 7 feet away. We were shouting like anything. Okay, all of us are girls, only 3 to 4 boys were there. So we were shouting. Then we stayed, like we managed to go nearby shore, like in the middle of the hill, like there were all rocks and all. We were staying over there. We literally at 12 o'clock in the noon or 1 o'clock or something like that, we were staying barefoot on the hilly rocks. Like you know how they will be, right? They'll be like burning, like they'll be just like a pan. Our feet is burning. Then we have to wait for 1 hour. Then another guy came, helper came, so he made us, like we went all the way around, and from then we came back onto the our meeting point. I'll show you pictures also there somewhere. So the thing is, never ever trust your friends whenever you are going to trip. That's what. I'll show you the picture. Snake inside the water, like it was a hilly area, ma. Like whatever the waterfall we went, it's very small one, Mallali waterfall. Like we had to go deep inside the hills. Like there were a lot of trees. Like waterfall, there is no water at that time. We went around October, November time. So it came like not a bigger one, a smaller one. So it came swimming inside. It's very, very, very small snake actually. I don't have a snake picture, but I have a picture of us before seeing the snake. After seeing the snake and all, we got scared. So this is the picture. Like we are a group of friends, and these are the four idiots who took us. These four are the four idiots who took us into water. So don't ever trust your friends when you are going for trek. Always have your backup plan. Yeah, that was there. And you know what we did? Like generally, college will give permissions like 2 to 3 days. They'll take care of everything. Only thing is you have to get permission from the industry. So what these guy did, uh, no, they did very cunning idea. They planned. They took an permission from industry in Bangalore, which is outskirts. Okay, so of the 3 days we have planned, one day went for Wonderla, the other day went for trekking. On the third day, like the last day at 7 o'clock or something, we have to return to Warangal. At 5 o'clock, you won't believe me. That on the day that we have to leave to Warangal, that is the time we went to visit the industry. Like hardly we stayed for 1 hour or 1.5 hours. That's it. Rest of the time we were just having fun. in Bangalore, Mysore, everything. Important, yeah. The most memorable incident is this one only, this trekking part actually. Mm. Yeah, that's it. That's the one interesting thing. A lot of things are there to say that happen in Coorg actually. I think you might have known, like it's a very beautiful place, very beautiful actually. That, yeah, it's beautiful. You should visit sometime. You might have already gone, but if possible, whenever you get into college, go with your friends. Like it will be memorable. And also in our college we have frequent trekking. So near Warangal there's one more hill point, like Pandavula Gutta, something like that. Even there also we went for trekking, and we had Bogata waterfalls, like some 100 kilometers from Warangal. So even there we went, but I don't have pictures of them in my drive. Maybe some other time I will show. But yeah, we went a lot of trekkings. We had a lot of cycle races, lot of. And even in Kajipet, like 10 minutes from our college, there's a hill point called TV Towers. Like it's the famous one. Like it's just like going to a coffee shop, like how frequent you will go to have a coffee or to get a snack. That's how people will go for this hill point called TV Towers. That will also be very beautiful in Warangal. Yeah, yeah, a lot of things are there. As far as I'm concerned, I went for these kind of things a lot, like this trekking, all these adventurous things. I have a thing for them. So whatever it might be, I'll just go. Even one time, me and the another girl, only two of us, and the rest of them were boys when we're going for this trek in Pandavula Gutta. So that's how we will be, like that's how spontaneous things will be when you get into college. So yeah, get into a good college. And these things they won't allow in all colleges. Only in NITs, IITs. In private institutes they do, but you do have some restrictions and all. You won't have that full on enjoyment. Means college you have to plan your career as well as you have to build some memories. So study properly, get into good college. And those who get admission, be it your like among you in NIT Warangal maybe next year, or among your seniors, like or your brothers and all who get into NIT Warangal, just let me know, because I have a lot of things, like a lot of interesting joints for food or for having some hangout places. A lot of them are there, I'll tell you, not right now, but crack the mains. Then when you get admission in the native Warangal, then meet me, I will tell you a lot of things. All right, so break time is done. Let's go back to class. One second, I'll share. This is our batch actually. I told you we went for trek, right? So this is me, this girl, and another girl, this girl. So we three went for trekking all of a sudden. And yeah, these guys are the idiots that took us into water, even if we were saying we don't know swimming. They got front and back after that. But yeah, they did. All right, chalo. Let's go back to lesson. One second. All right. So this is hydration part. Hydration in the sense we are adding water molecule, and that water molecule we are doing in two steps: addition of H plus and addition of OH minus. So electrophilic addition will happen first. That is, H plus will be added first to the carbon containing more number of hydrogen according to the Markovnikov's rule, and then to the another carbon, OH group will be added. If we are taking alcohol instead of water molecule, the alkoxide part, that is OR group, will be added to the carbon containing less number of hydrogen. So this is general hydration of alkenes. But there is another better method to perform this particular hydration reaction. Hydration reaction is nothing but the net groups, whatever they are being added, should be H and OH. So for that, take down another named reaction. This was asked how many times? This was asked only once in mains. So take this down. Oxy mercuration, oxymercuration, demercuration. Means addition of mercury and removal of mercury will happen. So oxymercuration, addition of oxygen along with mercury. Then in the second step, we will be removing the mercury, whatever we have added. So the net reaction I will write. After that, I will explain you the individual steps. So this is our alkene, and this is also, I told you, right, two-step reaction, which means we will be performing, we will be using two different reagent. First thing will be obviously mercury related product. So we will be using mercuric acetate, HgOCOCH3 taken twice, or CH3COO taken twice also you can write, and in presence of water we will be adding. And the second important reagent is NaBH, reducing agent. Okay, so our final reaction will be CH3, and obviously OH will be added. So this is the net reaction. Here also we are adding OH only. We are ending up with addition of H and OH. But this gives a better yield than the previous reaction. That is, by simply using acid catalyst, we won't get that amount of alcohol. So what we will be doing is addition of what is it in the bracket? Mercuric acetate. You can write it as HgCH3COO taken twice, or else you can write it as HgO C double bond O. Yeah, C double bond O CH3 taken twice. So the second type of notation was used in this particular compound. So you can, any of these you can write. You can write like this, or like this, or like this also you can write. All of them will indicate only one compound, that is mercuric acetate. So addition of alkene with mercuric acetate, addition of alkene with mercuric acetate in presence of water, because we are performing hydration reaction only, right, which means H and OH groups will be added. So in presence of water is called oxymercuration reaction, is called oxymercuration reaction. So what happens here is, we will be adding, we are telling that we are performing in presence of water, right? So the reagents that are finally added in the alkene will be H and OH. So the addition of H and OH groups will happen according to Markovnikov rule. Same thing, same rule, no other exceptions. So according to Markovnikov's rule only, the addition of H and OH will happen. And the main important thing for this is a better process for hydration reaction, better process of hydration of alkene. This gives better yields than the previous acid catalyzed alkane, acid catalyzed hydration. So this they have directly asked in the mains. The question also I have it, I'll give you after I explain this part. So just as of now, just take down the points. So this is a better process for hydration than when it comes to alkene. The reason also is there, I will let you know. Take down the model reaction first. So RCH double bond CH2. So the first reagent will be mercuric acetate. Yes, the reaction I gave you, right? So take down an example. Or how exactly does this happen? Wait a second. Take propene, CH3CH double bond CH2. So what is our first reagent? We are treating with mercuric acetate, right? So HgO, CO, CH3 taken twice. In presence of water, we are performing. So what will happen in the first step? The mercuric acetate will get itself attached to the alkene. So you have CH, okay, then you have CH2. So this is a skeletal reaction, right? So according to the anti-Markovnikov's rule, the H plus, the initial H plus will be added. So where it will be added according to the according to Markovnikov's rule, it will be added to the hydrogen containing carbon containing more number of hydrogen. But that will not happen right away, because whatever the pi bond that is broken down, it is happening in presence of this mercuric acetate. So in the first step, the mercury acetate will get itself attached, OCOCH3 taken twice, and you have OH, because hydrogen is not attached right away. Now in the second step, in presence of this reducing agent NaBH4, this addition of hydrogen will happen according to the anti-Markovnikov's rule. So what will be there? We will be having CH3, CH, OH, and CH2H. So this part will be removed, and instead of that we will be having hydrogen at the carbon having initially more number of hydrogens. Okay, so this is the final reaction. So we had prop 1-ene, when treated with mercuric acetate, the acetate itself got attached. Okay, sorry, this is only one Hg plus 2, right? It is in plus 2. One acetate group and one OH group will be attached initially. In the second step, in presence of the reducing agent, so sodium boride, boron hydride, we will be adding the H according to the normal Markovnikov's rule. So what do we got? 1, 2, 3. So propane 2-ol we will be getting. So this is the net reaction. So the type of question they have asked is, they have interlinked this question to rearrangement. Let me give it to you. Where is it? Here. I will give you the hint also how to do it. Shouldn't it be propane to Hg plus 2, Hg plus 2. No, only one, right? Hg is in plus 2 state now. So one acetate will be replaced. So this will be one valency and this is the second valency attached to the carbon. So Hg will be in plus 2 state only. This is -1 and the entire acetate will be -1. So Hg will be having plus 2 charge. Okay, so this was asked in mains 2003. JEE mains 2003 they have asked, and the question is phenyl group. Acha. Okay, this is related to alkanes part. It's okay. Once the alkanes is done, I will give the question. But the thing is, this oxymercuration, demercuration reaction they asked. They asked for alkynes. I thought I mistook it as alkene. Don't worry. While discussing alkynes, I'll bring that question back. So what is happening in this step? Initially, the mercuric acetate will get itself added. And in the second step, the reducing agent, that is sodium boron hydride, will add the hydrogen to the carbon containing more number of hydrogens according to the Markovnikov's rule. So for open chain carbons and all, we can perform this. So what happens for the cyclic alkenes? So when it comes to the cyclic alkenes, there are 2 points that should be noted down. Okay, so take a cyclic compound. So this is CH3, this is CH3. The reaction is Hg plus 2 in presence of water. You can write like this also, no problem. And the second is NaBH4. So this follows Markovnikov's rule. This is D, deuterium D. Okay. So give it a try. Where does the H gets attached and where does the OH gets attached? So this is our tertiary carbon and this is our secondary carbon. So hydrogen will attach to secondary carbon or tertiary carbon. It will be attached to secondary carbon, secondary carbon only, because we are following Markovnikov's rule, right? So secondary, very good. So we have deuterium already over here. To that hydrogen will get attached, and here you have CH3, and to the same position we have OH, because those two carbons are involved in the carbon-carbon double bond. So whatever we have this, whatever these H and OH are being added, cyclic groups, right? They happen in anti manner. Okay. So in cyclic compounds or in cyclic alkenes, addition of H and OH is anti-addition. In the sense, H plus will be added from one plane, OH will be added from the another plane. So anti-addition. Just make a note, that's it. No further details are necessary for this one. So this is same thing. Okay. One more note you have to take down here is there is no change when we were performing hydroboration oxidation. Instead of one ol we got two ol, whereas for this hydration reaction, even if we are getting involved a named reaction, there is no change. So whatever this oxymercuration demercuration reaction that we have, the product whatever we are getting is identical to hydration of alkenes. So no change. Whatever the alkene we get by normal hydration using acid as catalyst, here also we will get the same thing. Only thing is the yield will be higher. This is a better hydration reaction than the normal acid catalyzed reaction. So the first step is oxymercuration part. The second step is demercuration part. In the cyclic compounds, both the quaternary 1, 2, 3, 1, 2. Secondary only, na? They are not quaternary, right? How did you get quaternary? Please check, Nana. In the cyclic compounds, both the carbons are quaternary. No, this is tertiary. One carbon, second carbon, third carbon. This is tertiary. This is first carbon and this is second carbon. Only two carbons, it is secondary. Got it? This is D, not any other group. This is just deuterium isotope, 1H2, hydrogen isotope, deuterium. That's it. Okay. So this is about hydration reaction. So in tomorrow's class, we will do ozonolysis. Ozonolysis is very important. They have asked the question twice, and both the times they asked, it was very simple approach only. So we will be starting that in tomorrow's class. So please log in at 8 o'clock. I don't want to take class in the afternoon. So can we use OH for better in this reaction also? Can we use OH for better reaction? If you are referring to base, we are not using any base here. We are using a reducing agent to remove the acetate part. Okay, but the thing is, the yield, the amount of alcohol that we get at the end of this reaction and the way we get that, like it will be a better yield. If they say that this is better in terms of yield, they are talking. Okay, tomorrow also study our timetable they didn't give actually. Mostly they won't give to me because yesterday, only today there is only one, right? So please log in at 8 o'clock. I want to finish the rest of the thing. Ozonolysis is very important. After ozonolysis, the other reactions are less important, but we have to finish them because you never know, right? So we will do that in tomorrow's morning session. All right, that will be for today. I'll be sharing this PDF so you can refer to it, take your own points down. If you have any doubts, please get them to me. All right, have a nice day, Ma. We'll meet in the tomorrow's morning class. Repeat the note. Yes, 1 second. So OMDM is nothing but oxymercuration demercuration. So oxymercuration demercuration reaction is nothing but The products are the same products like we get in normal hydration using acid catalyst. Only, okay, I'll tell you the main reason for giving this note. So in the previous reaction, when we were doing a hydroboration oxidation reaction, we were converting alkene to alcohol. So one primary alcohols and secondary alcohols. Yes or no? To get primary alcohols, we used to get hydroboration oxidation reaction. To get secondary alcohols, we use the regular, the previous one. What is it? Diborate. Yeah, previous one, we used to get two alcohols just by treating with this one. Now, in this particular reaction, there is no such alteration even if we are using a different method. So both the hydration reaction using a mercuric acetate, that is Hg+2 followed by reduction process, both of them will give us two ols only, like secondary alcohols only they will give. So the main point for this note is there won't be no difference in the product. Only thing is they give a better yields. That's it. That's what we mean by uh, better hydration than the previous reaction. And OMDM is nothing but shortcut, oxymercuration, demercuration. Oxymercuration means addition of oxygen and mercury. Demercuration means removal of this mercuric part, mercuric acetate part. All right, that's it. That will be for now. Please go through the notes, revise it. Tomorrow we will see ozonolysis and the rest of the reactions. You guys have a nice day. Bye bye.